I was getting caught up with music there. Hi, I am Luis Anthony Ast, the video math tutor. Welcome to Basic Math. This is lesson number 1. This lesson concerns with how to identify what a number is, what type, what is the classification of a number, right? And the second part of this lesson deals with sets of numbers, okay, how to group, associate numbers together. Now, before we get started, make sure, of course, you've downloaded the notes and printed them up and had a chance to read through them. Okay? So if you haven't had a chance to do that, put this on pause, read the notes, come back here. All right? You did that? Okay, great. Before we get started, a small technicality. This is going to represent what I'm going to call, and what lots of people call, the real number line. It's just a line. I'm going to divide up in little bits and pieces. And the wonderful thing about the number line is there's what's called a direct correspondence between numbers, which I have right here in my hand, and number line. So for example, the number 1, if I place it anywhere on a number line, there is actually a point on the number line that corresponds right with it. And that point represents 1. Okay, I want you to understand that. Let's say I have the number 2. Put that right there. The number 2 has a point on the number line that, again, directly corresponds and is associated with the number 2. Now, with this in mind, we can now talk about numbers and how they are classified and how I can actually view them on a number line. So we're going to be doing that next. Natural numbers. Natural numbers are the numbers you can count with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Oh, sorry. We can represent the natural numbers with this symbol right here. Okay, it's a capital N, and it's rather stylized type. It has like a double bar through the center. And you'll see that in my math notes, and you'll see these in textbooks sometimes. Now, some math classes don't bother listing these symbols. If your book doesn't, then don't worry about it. Okay, but I will use the symbols. Again, natural numbers are numbers you can count with. On the number line, here's an example of how I can represent the numbers. And I can start with 1, and then I can start with 2, and then 3, and then 4, and then 5, and 6, and well, where am I going to stop with this? I'm just having too much fun here. I just can't stop. Oh, sorry. Well, you get the gist of it. They do go on forever. The smallest natural number is the number 1. Okay, so 1 is the smallest natural number. That's very important to remember that. Sometimes people are asked that on tests. Whole numbers. The natural numbers are fine for counting, but we're missing a very special number, which we need to take in consideration. And that is the number 0, right there. And of course, it has its corresponding point on the real number line. This collection of numbers are called the whole numbers. This is the math symbol for it. 0 is the smallest whole number that you can have. Be aware of that. There is no largest whole number. This goes on forever and ever. How you doing? Oh, sorry. Integers. Well, whole numbers are fine. You can do quite a bit with them. For example, hey, I can, count the big bucks here. 1, 2, 3, 4, 5, and 10, and 20. That's great. But, for example, if I look at my bank accounts recently, I don't see any of these things. I see a little dash and then a number. Like it's a negative value, they're called. If values are less than 0, in fact, let's look at that on a number line here. I've changed my numbers. So if I have 0, 1, 2, 3, 4 then forever, that's fine. But see, there's this whole other area on the number line which we have not talked about. Now, we want to talk about them. And that is where integers come in handy. The symbol for integers is a z. Why a z? I don't know. From Latin or something? I try looking it up. I can't find it. Maybe someone can write to me, but It's traditionally denoted by the letter Z. Again, it has this double bar with it. And now, let me take a moment to show you on a number line the other negative numbers. Well, here we see now the negative numbers on the number line. So if you take a moment here, this is how you can represent integers on a number line. And again, each dot represents each number. All right? And again, some people have a hard time grasping the concept of a negative number. Just think of it as a debt. Again, like my bank account balance. And let's look at another example. Rational numbers. Well, integers are fine for quite a few things in mathematics, but again, we have a slight problem. Not everything is a whole number that's positive or negative or zero. Okay, we saw that dollars, for example, is like a whole unit. But for example, with the United States currency, in case you're in a different country, this is some examples of the United States currency. We don't just have dollars, we also have a half a dollar or a quarter of a dollar. They're parts, they're smaller parts of a whole. Or 5 cents, a penny, a dime. We have different values that are actually smaller than 1 unit. On a number line, 1 unit is exactly the distance from one tick mark to the next tick mark. 1 unit, 2 units, 3 units, and so on. But what if I wanted to put, instead of a point right here from, 0 is fine, and 1 is fine right there, but what if I want to point, let's say there, in the middle, half? Well, we need something that would describe what a half is of something. And that's where rational numbers come in. A rational number is actually defined to be an integer divided by another integer. Well, the divided part can't be 0. That's technicality. The math symbol is Q for quotient. All right? And they're pretty handy to describe a great category of mathematics. All right? So, in a nutshell, what you want to remember about a rational number, it's an integer, for example, 3 divided by another integer that's not 0, like 7, for example. Okay? Now, you might say, well, this is a nickel. It's worth 5 cents. Well, 5 cents can be represented with dollars like this, 0.05. So it turns out certain decimal numbers, not all decimals, but certain decimal numbers are also rational numbers. Well, which ones? Well, definitely something like this, or let's say 0.25 for a quarter, 0.01, 0.10, 0.5. Now on paper, I like putting a 0 in front of all these decimals. So you'll see me do that quite a bit. And that's so I don't lose the decimal point. You'd be surprised how many times I write something like 0.5 and so you probably can't even see that. Okay? Or I write down 0.5 so fast it looks like a line. I think, oops, that's a -5. And I make a mistake and I get it wrong and life is not good. So I will try to put a 0 in front of my decimals. Now, what about other types of decimals? Okay. Let's talk about that next. Well, now we can see I've zoomed in a bit on the number line. There's my 0, 1, 2, the negatives are in this direction here. But now look what I did. I kind of subdivided each entire unit. Instead of each one being 1, 2, 3, this is 1, that's 2. And I would like to represent this point right here. Well, what is that? Well, it looks like we split this up in 3 parts. So parts of 3, and it looks like it's the 1, 2, second part of 3 sections. So I'm sure most people can recognize that to be 2/3. So fractions can be represented on a number line, and this is how it would look like. just 2/3, and you put a point there. Now, how can we represent this fraction in decimal form? Well, you put the 3 out there and the 2's in here. Well, 3 doesn't fit into 2, so 0. So I'm going to tack on a 0 and put a decimal point right there, and there's a decimal point right there. You say, well, how many 3 fits into 20? Well, 6 of those, 6 times, I'm going to do this, by the way, the American way of doing division. There's also European or Latin American way of doing long division. We'll probably say that for another lecture. But anyway, we're going to get 18. We subtract, we're going to get 2. And then we tack on a 0 here, a 0 here. And guess what? We're going to keep getting 20, 20, 20, 20, 20. And we're going to keep getting 6, 6, 6, 6, 6, 6, 6 forever. That's interesting. What does that tell us? Well, we know 2/3 is a rational number because it can be represented by an integer divided by an integer, not 0. I can place it on a number line, but its decimal representation doesn't stop like 0.5 or 0.25 like we saw earlier. It never ends. And notice, it's always 6, 6, 6, 6. Now, that always has to be the case, has to be exactly just the same number? Well, no. I can have another number, for example, 0.12120, 1212 forever. Or I can have, let's say, 0.357, 357, 357 forever. Okay? As long as it's a set number of repeating digits along the way, that's actually a rational number. Now, how can we represent these decimals in a more... Obviously, I can't write it forever. So the 0.666 forever can be represented with a bar over the 6. And this number over here, I can represent that with a bar over 1, 2. This can be represented by 3, 5, 7, and a bar over the 3 numbers. And that just means the number repeats itself forever. And that, in a nutshell, is what the rational numbers are all about. There's some examples of these. Okay? On the calculator. All right, at this time, let's break out calculators and learn a little bit about how to input our different types of numbers in here. Okay? So I have this mini cutout of the TI-84 plus Silver Edition calculator to illustrate this. First off, if you want to just type in natural numbers, all you really need to do is just type any of the number keys. That's pretty straightforward, pretty easy. Okay. If you want to include whole numbers, then make sure, of course, you count 0. Now, obviously, you use 0 for some natural numbers like 10, 1, 0. Okay. Integers would be the same thing, but we have an additional key to work with, and that would be the negation, negative key. It's right down here. Now, big warning, make sure you don't confuse this negation key with the subtraction key over here. All right, they're different. Okay. If you get an error on the screen, syntax error, you press the wrong key. Okay. With rational numbers, what we're going to do is you can input all your number keys again, but also now you have your division key to represent fractions. So if I want to put, for example, 3 divided by 5 in the calculator, I would just type in 3 divide by 5, and of course press enter. It's always a good habit to always actually also use the clear key that's up here to clear the display before you do your math operations. The answer for a rational number is always a decimal at first. Okay. We're going to learn how to convert fractions to decimals and decimals to fractions in more detail in the lesson that is titled Fractions. So we'll learn more about using the calc in that area at that point. Irrational numbers. So far we've looked at quite a few numbers: natural numbers, whole numbers, integers, and the rational numbers. There's another class of numbers that are called the irrational numbers. Well, what are those? Well, those are numbers on a number line that cannot be represented by an integer divided by an integer. Okay. Well, what's an example? Well, the most famous example of an irrational number is pi. No, not that pi. What I mean by pi is this number, pi. It's the Greek letter pi. And, well, what is that number? Well, that's the number that represents the number of diameters that fit on a circle. So if you have a circle right here, for example, and I have this diameter, okay, and if I were able to take that out and twisted it and placed it right on the circumference of a circle, how many would fit? Well, approximately 1, 2, 3 diameters, but there's a little bit left right here. Okay, well, people have tried, well, not tried, they have measured this, and you get approximately 0.14 additional diameters right there. Okay, so if someone asks, well, what's pi? I don't understand what pi is. Oh, just the number of diameters that fit in a circle. Easy, right? Oh, now that you know that, you can rest easily now. Well, great. How can I actually represent pi on the number line? Well, it's, well, let's say around right there. Okay. Now, I did not put the point 3.14. That's just an approximation. That I want to say that's really the exact value of pi. So actually, irrational numbers can be represented exactly as a point on a number line. That's a fact. Okay. What's another example of an irrational number? Well, if you've encountered what I call radicals, like square roots, cube roots, most of those are irrational numbers. An example of that is the square root of 2. Again, if you have not seen this type of notation, this number, I will cover that in another lecture. Okay, so, but if you have, great, you're going to get a good idea of where this is located. Well, if you punch this on your calculator, you're going to get approximately 1.4 something. And that's going to be some point on the number line, oh, let's say like around right there or so, approximately. Okay. Well, again, 1.4 is the approximate value, but again, I want to say that that's actually the precise value, at least pretend that is where my square root of 2 is located. And I'll say right here is my pi, okay, on the number line. Again, there are other examples. I talked about a little bit of that in the notes. There's a number called e, which is the natural exponential number. That will be covered again in detail in another lecture. So here's an example, a couple examples of what are irrational numbers. One last thing I want to talk about the irrational numbers is the symbol for it. It's J. Most textbooks don't make an effort to mention or list a symbol for the irrational numbers. Other books don't use the J. They just say, well, it's just everything that's not a rational number. It's the opposite of a rational number. And that's fine to do that. And I actually mentioned that in my notes. That you have different symbols, a Q with a little bar over, of a little curly tilde over the Q. That's fine, but it can be represented by the letter J. Real numbers. Well, one final classification of numbers that I want to talk to you about in detail, and that is the concept of a real number. All right? Real numbers are really just a combination of all the rational numbers and all the irrational numbers. The math symbol is this double bar R. Okay? In writing, the symbol is traditionally just written something like this. Okay? So if you had to write it down on paper, this is what you would do. And this is the most typical common symbol you'll see. Most of the others, maybe, maybe not. All right? But this one almost for sure, as an instructor, will slip it into class. So be aware of that. And again, a real number is just any number that can be represented on a number line. Well, earlier we talked about how to represent on a number line a specific integer or a fraction, a rational number, whole number. How can we represent all the real numbers? Well, that's easy. Just go ahead and shade in the entire number line. Just make it like a thicker line. That's all you got to do. Now that we've covered all the basic types of numbers, there really is one more thing we should worry about. And that's, well, what if something isn't on a number line? It's great to have a point, right there on a number line, but what if my point is now, well, there? It's not on the number line. Then what? That's a good question. Well, in that case, we have what are called imaginary numbers. And they're represented by a lowercase I, like this. So imaginary numbers are numbers that are not real. But that's okay in there a bit. If you have a hard time understanding what an imaginary number is, don't worry about it too much. Again, I have an entire different lesson that all we deal with are these imaginary numbers. If we combine this imaginary numbers with the real numbers, then that is what we're going to call complex numbers. This is the symbol for complex numbers. Again, I don't talk about complex numbers in detail in these notes. Again, that's saved for another lecture. But I want you to be aware of their existence. Another example of a complex number is very specific square roots. For example, the square root of -2, for example. I cannot put that number on a number line. It's not real. Okay? The inside, or the radicand, of a square root must be positive or 0. It cannot be negative. If it's negative, we can't do anything with it. Those are part of the imaginary numbers. Okay? I mentioned this, and I mentioned about the eyes, because sometimes on exams, a professor will give you a list of numbers and say, which one of these are real? And, well, you need to be able to identify, oh, if I see a square root of a negative number, and that negative's in the inside, I can't count that. All right? Or an I. If I see like a little lowercase I on the outside, all bets are off. Now that we know what all the natural numbers are, and the integers, and whole numbers, and all that stuff, we want to now be a little more formal with it. And for that, we need to introduce the concept of a set. A set is just a collection of objects. It could be letters and numbers. We usually denote a set by a capital letter. For example, how about OH? And we group the items within the set inside braces or curly braces. The actual items inside the set are called the elements of the set. And let's say I want to make this a set of all numbers I can count with one hand. 1, 2, 3, 4, 5. So let's actually write those in here. 1, 2, 3, 4, 5. That's a set. Now, important thing to know about sets is that there is no order, much like my apartment here. Sorry. There's also no repetition. I can't have 1, 1, 2, 2, 2, and so on. That's just one of each. All right? Now, if I want to say that 1 is an element of this set, I would use this symbol right here. So 1 is an element of set H. That's how I would read that. Okay. Now, we also have something called subsets. How about, let's call this F. And I want to make F to be the elements 1 and 2. So F is a subset of H because everything that's in F is within the H. Yes, we have notations for all this, but again, that's an entirely different lesson. I just want to give you the basics of what a set is for this lesson. Let's look at 9, for example. What set or sets is it a member of? Is it a natural number? Yes, I can count with 9. How about this one? Is it a whole number? Yes. Integer? Here's one for you to think about. Is it a rational number? Well, what's the definition of rational number? It's an integer divided by an integer. And yeah, I can rewrite 9 as 9 over 1. So yep, it's a member of this group. Because it's a rational number, it's not irrational. So no, not in this group. And all rational and irrational numbers and everything else before that is a member of the real numbers. So yes, this is also real. Here's another example. 0. Is it a natural number? No. Okay, the smallest natural number is 1. So you cannot put that in this group. Is it whole? Yes. In fact, it's the smallest whole number. Integer? Yep, it's an integer. Is it a rational number? Yes, it is, because again, I can divide by 1, and it seems kind of strange, but yeah, I can do that with 0. So it is a rational number. Of course, since it's not rational, it is not irrational. Don't go there. And because it's rational, it's also real. And we're not going to go here. Here's another example. Square root of 4. Now, when people see the square root, right away they go, that's got to be an irrational number. Irrationals have the square roots in them. And well, this is actually a trick question. So you got to be careful. See, this is really equal to what number? 2. So the moral of the story, when you have a test question, take a moment to look at it. So, can this number be rewritten in a different form? For example, this. Another would be like a fraction. Maybe a fraction can be reduced to a whole number. Okay. So now that we know it's really 2, it's a member of what group? Is it natural? Yes. Whole number? Yep. Integer? And of course, we know it's not irrational, it's rational. So we throw this card out the window, okay? So, and yes, it's also real, okay? Now let's talk about pie. Apple pie, cherry pie, pecan's pretty nice. Oh, sorry. It's lunchtime for me. No, this pie. It's a member of what set? Well, we talked about this earlier, actually. It's only an irrational number and real. That's it. Okay? I cannot represent pi as an integer over an integer. You might go, well, hey, I can do this to it, over 1. Yeah. Well, so, but see, this is not an integer to begin with. See, rational numbers are integers divided by integers. This is some really strange number, right? It's on the notes, written to like 99 decimal places, okay? So, no, it is not rational, but it is real. Oh, it's hot here. Oh, sorry about that. Here's our next example. Square root of -1. What's that going to be? Well, I talked about this earlier. It's a square root of a negative number. So, is it in here? No. 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 It's going to take a while. Nope. Niet. Only here, folks. Not even real. It's only considered a complex number. Okay. This is really the definition of the number I, the imagined number I. It is the square root of -1. So that's it. Now let's look at this number over here. 15/3. Well, a lot of students see this and go, hey, I know this. This is an integer divided by an integer. So this has to be a rational number. And they start off right there. Well, they're right, but again, don't just automatically just dump all fractions into the rational numbers and call it a day. What is really 15 thirds? It's 5. See, now we have to go back to the beginning. Is it natural? It is a natural number. Whole number? Yes. Integer? Yep. See, now we can say, yeah, it's also, I can say 5 over 1. So it's also rational, it's not irrational, and it is real. Yeah, pick a card, any card. Oh, let's do another example. 4 over 0. What's that going to be? You go, is that 0? Well, know which one of these it is? None of them. 4 over 0 is not even a number. It's undefined. We're not allowed to divide by 0. And if you go back to our formal definition of a rational number, it's an integer divided by another integer that's not 0. That's actually put in there as like a little extra. So as long as this guy's down here, can't do it. So this does appear on tests, and they're trying to trick you, so just don't include it. Now, if you had this, though, 0 over 4, that's okay. 0 over any number that's not 0 itself is 0. So we can deal with that. For our last example, be rather complicated. Look at this. It's also a very typical test question. Instead of just giving you one number like we've been doing, they can give you a set of different numbers, and then we have to decide, well, what group should it be classified in? So let's take a moment to look at these, and I want to figure out, well, which one first should be with the natural numbers? Well, let's look at this first one right here. Negative square root of 5.7. Well, natural numbers are counting numbers. 1, 2, 3, 4. That's not a number I can count easily with my fingers and toes here. So that won't be it. Negative 9 is, again, it's negative. I cannot count negative numbers as natural numbers. 0 over 2 is really just 0. In fact, I just talked about that. So 0 is not a natural number. 5 and 2/3, that's a mixed number. It's not entirely like a whole number that's not 0, though, okay? It won't work. What about this? Well, 0.3333 forever, that's what the little bar means, is really 1/3. And 1/3 is not a natural number. Pi squared is really not natural. Square root of 16. Now, a lot of people see the square root of 16. It's a square root. It has to be irrational. Again, they're trying to trick you. Square root of 16 is really just the number 4. And 4 is a natural number. So, we found our natural number right there. Are there any others? Let's see. 3i? No, that's imaginary. That's not even real. And 37/24? No. If I try to reduce that on my calculator, I get some decimal. In fact, try that. Just go 37 divided by 24. You get some decimal. So that's the only natural number. Let's talk about whole numbers. Well, we analyzed a lot of these numbers in detail in the previous discussion with the natural numbers. So I'll just cut to the chase. With the whole numbers, they have to be 0, 1, 2, 3, and so on. So looking at this list right here, that's 0 right there in disguise. 0 over 2. On a test, you should write 0 over 2 because it says 0 over 2. Although some professors will say, well, write in 0 instead. And of course, square root of 16 is 4, and 4 is a natural number, but it's also a whole number. So those are the only two whole numbers in this example. Now let's talk about integers. Which of these would be integers? Well, a good way to progress through this problem is anything we've done previously is going to actually be included in the next set, with the exception of irrational numbers. So all the natural numbers and all the whole numbers are also part of the integers. So the 0 and square root of 16, which is 4, are integers. But what else? Right here, negative 9. Negative 9 is an integer also. Now, which of these are rational numbers? Well, all our previous answers are included in this set. Okay, all the natural numbers, all the whole numbers, all the integers. So the -9, the 0, which is this number right here, and 4, which is square root of 16, are all a member of this group right here. Are there any others? Well, no, not that one. A, 5 and 2/3. You might go, well, that's not really an integer divided by an integer, but I can make it an integer over an integer. That's really 17/3. Again, how I did that is covered in our fractions lesson. Most of you should know how to do that anyway. So that is a member of our rational numbers. Anything else? Yes, right here. A rational number is an integer divided by an integer, but it's also decimals that just stop, they terminate, like 0.5, or a decimal that goes on forever, much like these lessons. Just kidding. Goes on forever, and it's a locked, set, repeating pattern of numbers. Okay, so that number right here, because of the bar over it, is a number that repeats itself forever, so it is also a rational number right here. Pi squared, no, that's not going to be rational, because pi itself is irrational, so its square is just more of a mess. And we can talk about that. It's okay. I's are not. And look at this guy right here. 37/24. That's an integer divided by an integer, so that is also a member of the rational numbers. Now let's see which one of these are irrational. Negative square root of 5.7 is irrational. In fact, try punching the calculator. You get some decimals, really weird numbers mixed along there. It's irrational. And some of you might go, well, wait a minute. You said earlier that square roots of negative numbers are not irrational. They're imaginary. So that's why this is a very tricky test question. That's why I have it here, so you can be more aware of this. The negative has to be inside the radical, in the radicand. If the negative is on the outside, that's okay. That just means it's on the other side of the number line. It's in the negatives. But it's still an irrational number. It's fine. Okay, but if the negative were on the inside, that's bad. Are there any others? Yes, right here, pi squared. If you're not sure what pi squared is, again, just type that in your calculator. And it's a really messy number. Any others? No. That's it for now. Now, which of these are real? Well, pretty much everything we talked about so far that you've written down is a real number. So the negative square root of 5.7, the -9, 0 over 2, 5 and 2/3, 0.3 forever, pi squared, square root of 16, and this number right over here, 37/24. The only one that's not a real number is your 3i.